So here's a fresh start. All right. Cool. So other questions, comments?
You told me to bring up the whole, if you put the data in
Yes.
thing in the wrong order.
Let's try this. Come on. All right, let's make a pair of structures. All right, I got a pair of structures, node 1 and node 2. And my main program, I'm going to declare node 1 and node 2. And let's look at this in GDB. I forgot a semicolon, didn't I? I forgot 2 semicolons. At the end of what? Oh, yeah, yeah. My computer's officially going to die. I'll reboot it at the break. It's been acting flaky all morning. I think it just needs a reboot. Not very often, I just hibernate. But my CPU is at 100%, my RAM is at 67%. So something bad's going on. Yeah, I should. That shouldn't be taking CPU or RAM, though. All right, so I'm in my program, and I'm about to do my print statement. So I've already declared A and B. So if I print A, that looks like this. If I print B, it looks like this. I don't know if this is going to work. Let's look at the address of A.data. That's 62CC28. Oh, it's not going to work because I didn't do what I wanted to do. So the question is, what happens if we change the order of these things? So if I just print, right, it shows me my data first in my struct node 1, and my node 2, it shows me next first. Let's look actually at the addresses. Address of A.data is 62CC28. And next comes 62CC2C, so that comes after the data. If I look at B, my data is stored at 24. And my next is stored at 20. So it's definitely storing my pieces of my structure in the order in which I declared them. Okay. Now, let's make a function. And let's print the data piece of our node. So function fun is just going to take a struct node star, and we're just going to print out the data piece. So let me prototype that. And let's set node a.data equals 42, a.next equals null. And let's pass the address of a to our function. All right, so you got the setup. We have a struct node. A is a struct node. We set the data to 42. We set the next to null. We pass its address to our function. And our function will take a struct node star, that's the address of A, and print out the data piece. But we've declared the structure with the fields in the opposite order. So if this does what I'm thinking it will do, the heck was I doing there?
I was wondering, I was like, you can declare it to return a function.
Yeah, right. All right, I'll be clean. Yeah, let's make it void. It's not even over yet.
At least it's fried.
Yeah. Wow. So where's that coming from? I've been doing something, I guess, in my brain. Maybe functions from 215. I don't know, I'm in some quirky mind spaces these days. I went to a violin class Monday night, and I haven't played violin in front of anybody for like 40 years. So that's probably got my brain in weird places. All right, so let's run this. It should print the value of a.data, which we set to 42. But when we run it, it's actually going to print a 0. Right? And that's because in our main program, we said, here's my data, here's my next. In the function fun, we told it that the first thing is next, the next thing is data. So when we said print data, it printed the second piece of that structure, which happened to be the next from main. So if we had simply swapped the order of those, then it'll do what we want. Uh-oh, I got the gray screen of doom. Come on, 42. Come on. Yeah.
It's a big program.
It is. It's going to print the answer to everything. There we go. All right, does that make sense? So the order is definitely critical. And the reason, I don't want to try to go into it with this kind of laptop issue right now, but the reason is that once you compile your code, assuming you don't do a -G switch, this notion of this is a struct node, this is a struct something else, that's completely gone. Right? The only thing that's stored is binary code that corresponds to what your C program was asking you to do. So if you have a structure, You have a structure with a data and a next. And you have a variable temp. When I say something like temp arrow data, that's going to translate into assembly language and into machine code that basically says, take the address of temp, add nothing to it, and get what's at that location. So this will be basically the thing at the location given to by temp, because temp points to our data field, which is followed by our next field. When I say temp arrow next, the compiler looks at this structure and it's decided, okay, this is going to go at an offset of 0. This is going to be stored at an offset of 4. And so this will translate into accessing whatever the value of temp is plus 4, the thing at that location in memory. And so in my function, when I try to access my next field, this is what I'm trying to access. And if some other structure is using this to represent data instead of next, right, it's got no way of knowing. So all of those names have kind of gone away by the time you get to an object. Certainly by the time you get to an executable. How's my CPU doing? Not looking good.
So if you do them in a different order than what we've been declaring,
As long as you're consistent, you can do it any order that you choose, yes.
I probably just with the ODP, so you're using this.
Right, yeah. Yeah, and I need to make sure I mention that in the future, because then it's actually fixed. And you can usually avoid getting into trouble on your own stuff by just using a .h file. So all your structure definitions can go in one include file, and you just include that everywhere. And then you should be consistent. All right, I got to take care of this. So I'm going to close this out. I'm going to close this out. What else can I close? I'm going to close this out. My CPU is still pegged. So other questions, comments?
I guess ideally, I asked you about free yesterday, so during delete you're going to be freeing whatever your current node is.
During delete, you definitely want to free.
At the very end in your main function, is that when you want to free the remainder?
Yeah. So you've got to free when you delete, otherwise you have no way to go back and free it later, because when you delete it, you removed it from the linked list. There's nothing pointing to it, unless you like saved those somewhere. And you can't remove the nodes that are part of the list until you're done with the list, which is only at the end of the program. So delete things and free those nodes you're deleting, and then at the end of the program, when you say exit, call some function that just frees everything that's allocated.
So we should make a stack that stores all.
Make a stack that stores all your nodes. No. But you could do that. All right, I think my PC is getting a little happier. All right, any other questions? Let's talk about queues. So we talked about stacks on Monday. Stack was a last in, first out. The last thing that you put into, the most recent thing you put into the stack is going to be the first thing that comes out of the stack. So you're pushing things down and you're popping them off from the stack. A queue is a first in, first out. So the first thing that goes in a queue will be the first thing that comes out of the queue. And the physical model, if you want to keep one in mind, would be something like a checkout line, a bank teller line. Okay, some kind of line where people are queuing up First person in line is the first person who gets taken care of. Next person in line will be second. Last person who comes into the line will be taken care of after everybody in front of them has been taken care of. DMV. DMV is like first in, nobody out. Actually, DMV in Washington I think is great. Back east, like Virginia, it's like bring a lunch, you know. Seems pretty good here. Yeah. All right, so first in, first out. So what does this look like? Drawing queues is a little tricky because things kind of move around. So let's say we insert at this end and we remove from this end. Okay, so let's add the number 2. Well, we'll put a 2 into this end. We can think of this as like a pipe. And the 2 goes all the way to the front of the queue. And it's sitting there. Now, if we were to remove something from the queue, we'd remove the 2. But if we add something before removing, let's add a 3, that's going to go in right behind the 2. And if we add another thing, that's going to go in right behind the 3. And now if we remove, that should give me back my 2. So the 2 should get removed. And in a physical queue, right, everybody moves up. So this becomes a 3 and this becomes a 4. But it's a pain to keep redrawing my queue like that. So I'll generally just sort of let things move around in here, but we'll understand that the thing we're removing is whatever is the rightmost number that hasn't been removed yet. So let me put my 4 and my 3 back, and I'll just remove them. So we remove the 3, we remove the 4. So those are gone. All right, so terminology. Bless you. There's a head and a tail of the queue, head of the line, back of the line. So the head of the queue is where we're removing from. The tail is what we're inserting into. So add at the tail and remove from the head. There's occasionally some ambiguity in those terms, but most of the time this is what we mean by head and tail. Tail is where you add, head is where you remove. But I have seen cases where those are backwards. So make sure you know what the definitions are. For us, we'll stick to this consistently. All right. Well, right now the queue is empty. There's nothing in there. If we start adding things, we start filling up these spots. And we remove, we can start emptying these spots out. It's possible that your queue will fill up depending on how it's implemented. Okay, in a physical line, you can get to the point where you're at the end of the, velvet ropes that are marking off where people should queue up, and everybody's jammed against the door and you can't get anybody else in the building. The queue is full, right? Empty queue is pretty straightforward. There's nothing in the queue. So nothing has been inserted that hasn't been removed. All right, so why do we care about queues? They're useful in a lot of different situations in computer science. So one example would be process management. And typically in an operating system, there's something called a process queue. So here's the idea. You have a computer, single CPU, single core. Let's keep it simple. You've got 10 different people using it. Think our Linux server. somebody's running VI, somebody's running GCC, somebody's testing their program, somebody's playing Rogue. Everybody's doing different stuff at the same time. And it looks like you're all executing simultaneously, but in fact, you're not. In fact, that computer is only doing one thing at any given time. It's executing one assembly language instruction. Okay, forget about pipelines and stuff. It's basically doing increment this memory location. Compare that memory location to 0. It's doing one thing, which means it's working on one piece of one person's program, or maybe one piece of some operating system function, updating the time because the second counter just ticked, or receiving a packet from the internet. And it's all it's ever doing, one thing at a time. But it looks like you've got multiple processes running simultaneously. So let's imagine we've got 3 processes. Well, let's imagine you're doing something on the CPU. So your process is running, okay, and you're called process 1. And somebody else decides to run a process, and that's process 2. Well, it has to share the resources between these 2 processes. So basically, there's a queue, and process 1 and process 2 are 2 entries in that queue. And forget about where this starts, because the startup is a different issue. But suppose process 1 is executing right now, and process 2 wants to execute, so it sits inside this process queue. Your job runs for a few milliseconds usually. And there's a timer, and when that timer goes off, the system says, okay, process 1, you're done for now, back of the line. So it takes all the essence of your process and it puts it in the back of this queue, and it removes whatever's at the head of the queue, which is process 2, loads that into memory, sets all the variables back to where they should be, and says, go ahead and execute. And it starts its timer. And now process 2 runs for, say, 10 milliseconds. And the timer goes off, operating system says, okay, process 2, you're done, saves all of its current memory contents back of the line. Process 2 goes back into the queue behind process 1. This can be horribly expensive. Fortunately, 10 milliseconds is a really, really long time. Okay, if it takes a nanosecond to do an instruction, that's 1,000 instructions per microsecond. It's 1,000,000 instructions per millisecond. So 10 million instructions before this whole process kicks in. That's pretty generous. All right, so process 1 comes out of the queue and starts executing, and while it's running, process 3 says, hey, I want to do something too. So the part of the shell that says, okay, you're trying to run program 3 ultimately causes this process to go into the process queue. Process 1 finishes, its 10 millisecond quanta goes into the back of the queue. Process 2 comes off and executes for a while, goes into the back of the queue, and now process 3 is going to get a shot. Okay? Process 3 didn't get to run until the job that was currently running and all the jobs that were queued up behind it, that was process 1 and process 2, until they came out of the queue. Okay, that's this FIFO thing. It's also LILO, last in, last out. So process 3 runs, goes into the back of the queue. Process 1 runs. Suppose process 1 finishes, it just doesn't get put back into the queue. And now we've got 2 things in our process queue. Process 2 will run, go into the back of the queue. Process 3 will run, go into the back, and so on. So that's a very common application of a queue, is to manage jobs. And in most operating systems, you can actually poke around the memory of the operating system and find an actual queue implemented somewhere. And if you look at the entries in that queue, you'll see process IDs. And you can follow those IDs and eventually find your way to the code and the data of whatever program is associated with that process. Can't do that without administrator privileges, otherwise that's a security problem. But on your own system, you can actually do that, and it's a fun way to sort of take apart how the operating system is doing its thing. All right, if process 2 finishes, right, it comes out and it finishes, doesn't need any more time, and then process 3 runs and doesn't need any more time, the process queue is empty. So usually there's something like a null job. On some systems like VMS, is actually a process called null. that's always ready to execute, but it's very low priority. And so there's always something sitting in the queue. It would throw the null job in, and then it would pull that out, push it in the back of the queue after its quanta, and then it would pull it out again, so you'd never have an empty queue. So you can do tweaks like that. Another thing you can do is you can have multiple queues with different priorities. You can have a low priority queue for user jobs. You can have a high priority queue for system jobs. You can have a very low priority queue for what are called nice jobs. On Unix, you can say nice command and it'll run it at a lower priority. So you can be nice to other users. And so the idea would be you check the high priority queue first. If that's got a job ready, you go ahead and execute it, push it in the back. If that queue is empty, then you check the medium priority queue and so on and so forth. So that's an application of queues in operating systems.
Pretty much like the high and low interrupts.
Yeah, yeah.
You make something super high priority with a command like me or something?
You can do a, I don't remember if it's positive or negative, but you can do a different sign on the niceness, and it'll make it a high priority. And if you make it too high priority, you'll cripple your system, right? So that's fun to do. And the system jobs, I don't remember what priority they run at, but you can do a man space nice and see all the details. And on the server, you can nice your jobs down to a lower priority. On your own system, you can nice them down or up and experiment. All right. Back to 224. Right, you remember pipes? So we have one command, we pipe it into a second command. And the idea was this is generating output to something we call standard out. And command 2 is receiving input from something called standard in. So every time it says get car, it's reading a character from standard in. If I just run command 2, it's waiting for me to type something on my keyboard. If I say command 2 less than file, it's reading from that file. If I say command 1 pipe into command 2, standard in is actually coming from standard out of command 1. So here's a way to visualize this. Command 1 is pushing things into this pipeline. And the other end of this is going into command 2. This is standard out. This is standard in. Well, what is this thing in between, this pipe as we call it? It's just a queue. The first character that command 1 generates will be the first character that command 2 ingests. This might print 50 characters, printf, blah, 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 blah. And if I say get a single character, it's going to get that first character that command 1 printed. And if I say get a second character, it's going to get the second character. And if before I say get the third character, command 1 prints some more stuff, that all gets queued up behind the stuff it already printed. And if I keep saying get characters in command 2, it'll keep reading in all of the first set of stuff that got printed, and then it'll start reading in the second set. Right? And this makes perfect logical sense. A stack model of first in, last out would not make any sense for a pipe. Right? Because when I typed something, it would read it in the reverse order. Right? Which would be weird, but it would be fun to do. It'd be fun to try to work with that. So this is a very natural model for basically buffering things up. And buffer and queue are sometimes used to mean the same thing. Right? The idea is you can put things in here, but you don't have to pull them out right away. When you're ready, they'll be waiting for you. And the same thing when you use printf and you don't have a new line at the end, any output that you generate goes into effectively the same pipe. So you say hello, there's HELLO, and this is connected to ultimately you're displaying putty. But it may not actually come out until something forces it out of this pipeline, like a flush, right? Or if I've halted my output on here with Control S, then this is just queuing up. And when I hit Control Q, which says resume output, first I see the H, the E, the L, the L, the O. So queues are common in that setting also. All right, so you got the basic idea how queues look as far as their behavior. So let's look at implementation. And first I want to look at implementation via an array. So just like a stack, we can use arrays, we can use lists, we can use other things. I want to look at the array implementation first, and it's a little different from a stack. It's actually a little trickier than implementing a stack in an array. And for PA3, you're going to use a list for a queue. You're not going to use an array, but it's still good to practice on your own doing this with an array instead of a list. And if you write PA3 with a separation between user code and implementation, you can take your main code and rewrite your queue routines on your own to use an array and just relink everything, and it should work. So, and I definitely recommend experimenting with that. It's good fodder for exams, but it's also stuff you'll encounter down the road in future courses. It's stuff you're likely to hear during interviews. There's some decent questions that come up around queues and so on. So even though we're not doing this for PA3, right, it's good stuff to know. So let's picture our queue as an array. And it's going to be a small array. It's only going to have 5 spots in it because I want to keep things simple. So I'm going to make an array of queues, an array of ints, and I'm going to define a size variable to be 5. So pound define size 5. And suppose I want to add a 1 to my queue. All right, we insert at the tail, we remove from the head. Okay, so the first question is, where is the tail of this queue? Well, it could be anywhere, but we need to know where it is, right? So I'm going to have a variable called tail, and I'm going to initialize it to 0. And so to add a 1 to my queue, I'm going to store it at the location given by the tail, which is right here. So my tail equals 0. I want to store it here, but the next thing that I'm going to add, I want to store at location 1, right? So I'm going to increment my tail after I store. So queue index tail plus plus equals whatever number you're storing. That's our basic add function. If I want to add a 2, I store at the index given by tail, and I increment the tail. If I add a 3, store at the index given by tail, increment the tail. Let's add one more. Add a 4, store at the index given by tail, increment the tail. Now suppose at this point I want to remove one thing from the queue. So I'd like to remove the 1 because that was the first thing I put in. But I don't have anything that tells me that the first thing I put in was a 1 and that it was at index 0. So I need a second pointer, and we're going to call this head. And head's where we're going to remove from. So head is equal to 0 initially. When we say remove, we're going to read the element at index 0, which is a 1, and then we're going to increment head to a 2. So we remove the 1, and now head's equal to 2, which means the next time we remove, we'll pick up the 2. So our algorithm is basically Q bracket head plus plus. And this is one way that the FIFO structure jumps out at you versus a LIFO, because for both operations we're incrementing. With a stack, we were incrementing for one and decrementing for the other. So if we remove again, we look at the value of head, that's equal to 1. We return the value at index 1, that's a 2, and we increment the head. Okay, let's add one more. Let's add a 5. So where's the 5 going to get stored? Say again? Where's the tail? 4, right? So store it at element index 4, because the tail is 4. This is where the 5 goes, and increment the tail. Okay, let's look at what we have right now. How many things are actually in our queue? There's really only 3 things. We added 5 things, but we've also removed the first 2 of them. So our queue actually only goes from index 2 to index 4. Right, we remove the 1 and the 2. If we say remove, the next thing we're going to remove is index 2. That's the number 3. So our queue is not full. We've got 2 empty spots in here. But if I were to say add 6, and I just say store at the index given by tail, I'm going to be trying to write into index 5, which doesn't exist. Okay, it's out of bounds of the array. It could seg fault. Where would I like to store a 6? We could store a 6 right here. But we can only do that if somehow the tail was 0 instead of 5. So when we add to the queue, we're going to do a second operation. If the tail is equal to the size, set it equal to 0. So now after we added the 5, tail got incremented to 5. It should have gotten reset to a 0. And now when we say add 6, we store at the index given by tail, and we increment tail. I'm off screen. So we store at index 0, and we increment tail to a 1. Does that seem reasonable? All right, let's remove. So remove, look at the value of the head. It's a 2. Give us the element at index 2, which is a 3. Increment the head. Let's remove again. Head's equal to 3. Give us the element at index 3. That's a 4. Increment the head. So So what does our queue look like now? We've done a bunch of adds and a bunch of removes. What the heck is going on? Well, the tail is where we're going to add next, right? And that's right here. So our queue actually begins at the head. That's this entry right here. And it ends at this one, right? So it's wrapped around. If our array was bigger, this would simply be where the head was and the tail would be the next location, right? But because our array has a fixed length, we wrapped it around and our queue is up there. So it's not always the case that your tail and your head are in the same relative position to each other. They can flip around. And that can make queues confusing sometimes. All right, let's add a 7. So add, look at the tail location, it's index 1, that's where the 7 goes. Increment the tail to be 2. And now our queue extends all the way down to here. And we can keep doing this over and over and over again, as long as we don't add too many things without removing a few things. And the part of our array that represents our queue will sort of shift down and at some point wrap around, and then at some point wrap around again, and go like that, right? That's fun to debug.
Is there going to be a similar if statement for head?
Yes, so let's remove one more. So we return the element at index 4, that's our 5, and then we increment the head. But if we try to remove again and we try to read from index 5, it's going to blow up. So when we increment the head, we also need to say if head equals size, head equals 0. So our head actually wraps around back to 0. And now the next insert will happen at location 0. Sorry, the next read at location 0. The next insert at location 2. So what does our queue look like now? The tail is where we're inserting. I don't even know what we have in our queue anymore here. It's one of these things, if you actually think about it, it gets confusing.
I think it's just the top.
So, yeah, we're inserting at the head. And we're removing from the tail. No, we insert at the tail, we remove from the head. So tail is 1. All right, so this looks exactly like after we had just inserted 2 things into our queue. All right, let me talk about full queues, and then we'll take a break. So we can keep doing this process, and if we remove frequently, we're fine. So let's add 7 and then 8 and then 9 and then 10. Okay, so we put a 7 in here, and tail went to 1, put in an 8, goes to 2, put in a 9, goes to 3, put in a 10, tail is equal to 4. All right, if I try to add one more thing, like an 11, I would say store that at location 4, increment the tail to a 5, set it back to 0. There's one problem with this. I've got 5 things in my queue, but my head and tail are the same value. They're actually the same value that we had when we first started this whole process. Head and tail were initialized to 0. And the easiest way to tell if your queue is empty is just to see if head and tail are equal. But if we use this approach and we actually fill up the entire queue, head and tail are still going to be equal. Now we can set a separate flag to say the queue is actually completely full instead of completely empty, but in fact the easiest way to manage this is just don't allow the entire queue to be used. Let your tail get up to 4, but if I try to add one more thing, refuse. Say, sorry, the queue is full. And now the only time head and tail will be equal is when the queue is empty. And the queue will be full whenever head, sorry, we're inserting the tail plus 1 equals the head, or 0 if tail plus 1 equals size. So if adding one more thing will cause tail and head to be equal, we say the queue is full. And it's just, you lose one potential space inside your array, but it makes your code a little easier. So usually this is how it's done, because then you don't have to differentiate between this case where it's empty, this case where it's full. So this whole add 1 to tail, and if it's equal to size, set it equal to 0, we can clean that up as follows. We can use a modulus operator. So this says increment the tail and then reduce it modulo size. As long as it's less than size, it doesn't change it. You just get tail plus 1. But if this is equal to size, you'll get 0. Right? Remainder when you divide size by size. So that sort of takes care of that wrap over automatically. And any time that we were saying tail plus 1 or head plus 1, we can just put that modulo at the end, and it'll clean things up. So now our condition for is full is tail plus 1 modulo size equals head. And same thing, if we remove the 7 and the 8 and then we add an 11 and a 12, right now the queue is technically full, because this is the next position that we're going to add to. This is the position that we're about to remove from. And tail plus 1 is equal to head. So tail, next location to add, head, next location to remove. All right, let's take 5 minutes, come back. We'll talk about PA3. And then we'll talk about implementing this with linked lists.